Uh, I'm Tom Cheatham, professor of computer science at Harvard University, and it's my pleasure to be here sitting in front of Whirlwind at the Computer Museum to talk with Dr. Hal Laning. Well then, Hal, why don't you
Okay,
give us a little personal background here.
I started out life as a student in chemical engineering, graduating from MIT in 1940. I went immediately from that into pure mathematics for a year, and then spent about a year and a half at Brown University in applied mathematics, jumping from there at the early part of the war to the Watertown Arsenal, where I worked in the field of applied mechanics for 3 years. It turned out that the fellow to whom I reported at Watertown Arsenal was a close neighbor of Doc Draper. In fact, they shared kids from time to time, I was told. And anyhow, when the end of the war came about, I, in the fall of 1945, wanted to go back to school to finish up my doctorate. So my boss referred me to Doc Draper, and I started work November 1st, 45 as a, I guess they called them research associates in those days. Basically, it was a graduate student position. At that point in time, I was part of a mathematics group, so-called, of probably a half dozen people altogether. As I mentioned before the taping, we were rather informally organized, so that when the MIT professor who was running the group went back to full-time teaching, they put me in charge of the group. Unfortunately, they didn't tell me for about 6 months that this was the case. I had to sign a requisition, and I didn't think I was the one that was supposed to sign it. And I had this pointed out to me. At that time, the lab was about 60 or 70 people, I think, something of that order of magnitude. And from applied mathematics, we went through a period where I had 20 to 30 young ladies punching desk calculators as a computing group, through a mode in which we took on analog computers, and from there eventually took the plunge into digital computation. Our first venture in digital computation actually was 2 or 3, sometime around 1948 or 49 with the Howard Aiken's Mark I computer at Harvard. However, that was one of the, you write the instructions, we'll pass it through the wicket and give you back your results type operations, of course. From there, we moved eventually to running the MIT's Rockefeller Differential Analyzer for some component of our problems, and the IBM card program calculator, eventually the IBM 650 computer, which was our first in-house object that I would call a real computer. In the meanwhile, in 1952, we initiated this activity on Whirlwind, which eventually resulted in a successful demonstration, if you like, of the feasibility of algebraic compiling.
Why don't you tell us a little about your background with Whirlwind and the first higher-order programming language?
Well, at the time I entered the Whirlwind picture, it was early 1952, and we had struggled for quite a few years trying to do computation by more primitive methods, such as a room full of young ladies punching desk calculators. In the summer of '52, I got the bright idea that why couldn't we train the computer to translate mathematical equations into something that it could use directly. This culminated, this was done with the benefit of a number of skeptics amongst my colleagues and others, but we tried this on Whirlwind with a result that would be described as successful probably the beginning of 1954. Draper Laboratory, as it is now known, was at that time part of MIT, known as the MIT Instrumentation Laboratory. And under Doc Draper, who was the head of the Aeronautics and Astronautics Department, the lab was engaged in the development of a variety of equipment for fire control, for gunfire from ships, aircraft. Also, what has subsequently come to be known as inertial navigation, such as you find in your ordinary commercial aircraft these days. The lab was not predominantly involved with or interested in mathematics or computation or computers per se, but we were also, however, given a fairly free hand to do what seemed to be necessary to be done. And after trying to program the Whirlwind computer in its own assembly language, I concluded that something better has got to be developed if this is ever going to be directly used by engineers. In those days, by the way, there was a perception that the world was divided into classes. There were engineers and mathematicians on the one hand, and there were programmers on the other. It had been my firm belief, since I happened to fit someplace in the middle of this category, that instead of me as an engineer writing a program and passing it through a little wicket to a programmer who would then go off in a vacuum and program his interpretation of what I had given him, it would be an awful lot better if I could do it myself. And that was a very dramatic philosophy in those days, because it was not shared by the community at large by any means. That's what we did at Draper Laboratory, however, in the form of this initial compiler, and more importantly in the form of a later compiler that we developed for other commercially available computers. I think it made a difference, for example, in the Apollo program. That
would not surprise me at all.
Along about 1973, the Draper Laboratory was kicked out of MIT, at which point it transitioned from the MIT Instrumentation Laboratory to an independent, not-for-profit organization named Draper Laboratory after its founder and then-time president. That's what it is, of course, known as today.
Well, Hal, it's a real pleasure to talk with you about what's apparently the first higher-level programming language back for Whirlwind at MIT in the early 50s.
Well, it's a privilege to be here, and
you showed
it
me
was a fun time.
a few minutes ago some actual input.
Yes.
In those days, you managed to have actual subscripts and superscripts.
Well,
subscripts by
subscripts by a rather artificial convention, but yes, it
must have worked. So the language would appear to be something very much like the early Fortran, except with these subscripts and superscripts. And apparently then went on to be implemented on the IBM 650.
Yes, that's correct.
And the IBM
well,
701, 702.
Yeah, although the latter languages were really a totally different development, although they stemmed out of the program on Whirlwind, which we called George, by the way, under the the old saw, let George do it.
Yes, right. I see.
The other one was named Mac for reasons which are obscure even to me. It bore no relation to the Mac operation at MIT, which was the interactive terminals. But I don't know, mathematical algebraic computation or some such phrase, but I can't pinpoint it.
Mm-hmm. So it must have been quite a challenge to, for example, build a parser.
Well, because I didn't know what I was doing, it wasn't as hard as it might have imagined. Some of the formal rules I was totally unaware of.
Well,
And,
I think they didn't really exist at that moment in time. It was a little later that we actually had formal rules. I had the great displeasure of writing a parser about that time period with no notion of formal underpinnings or anything.
I lived in the terror that somebody would write a perfectly rational looking expression that I couldn't do.
Ah, don't doubt that at all.
But I lucked out, I guess.
Now, did your project have this? Well, John Backus's Fortran. I know one of the really driving concerns there was getting good, efficient code out.
Yes.
Because he was told that nobody would use this unless the code was really efficient. And he had statements that the frequencies of execution of branches and so forth,
Right.
which they quickly took out. Did you have that kind of overriding concern too?
Absolutely not.
You didn't?
No, in fact, the inefficiency of the language was one of the reasons that it never got developed any further, even on Whirlwind. One of the reasons was that we started with a machine that had 1024 words of 16 bits.
Wow.
Now, much of the central logic of the thing was written in that framework. By the time it became operational in any sense, they doubled the memory so that we
2048. Wow.
had room for an interpretive thing to do floating point arithmetic and so forth.
Right.
But because of the space limitations, each single equation, each single statement was read in from the drum independently and executed, which made a very painfully slow operation.
I can imagine you had to devote your memory to data, not the code.
It was fast enough to be useful in 2 or 3 instances, but it was nothing that, I mean, Backus would have turned over, well, he isn't in his grave, but IBM would never have accepted it.
I see. Well, of course, by the time he came around, there were 32,000 words of memory. I think,
Yes, yes.
machines he was using. So that's quite a different ballgame.
It is quite a different ballgame.
And how many people were involved in the project?
Myself and Neil Zerler.
Mm-hmm.
Neil was, my memory is that he was brought into the project well after it had begun, but he was my outside interface. His job was more than that of Gopher and less than that of an originator. He provided the floating point interpretive routines and explained to me patiently time after time how to operate in conjunction with Whirlwind.
Mm-hmm.
And he collaborated with me in some combination or other on the manual that we finally wrote on the thing.
Uh-huh.
But it was just, so far as I can remember, it was just the 2 of us.
Quite a project for 2 people,
Well,
particularly in those days.
it wasn't, as I showed you the code, it wasn't all that big.
Right.
But it was, well, I learned how to write tight code, as I'm sure you did in your day.
Oh, yes. That one did learn in those days, didn't it?
Speaking of the 650, I wrote the operating system for our operating system for the 650 in 100 words of 10 decimal digits each.
100 words.
And it operated with...
Unix these days is what, a million?
I have compilers, I know what you mean. I have operating systems. But that one was interesting because, among other things, we knew that RAMAC, the disk drive, was coming down the pike, although it wasn't available yet. So we used mag tapes as direct access devices.
Mm-hmm.
there was some combination of tape records and what do they call them? Something marks. At any rate, something to indicate end of record. That let you position a tape directly to a particular block of information and read it in and write it back and so on without things drifting into each other, which was, of course,
If
one
you're
of
willing
the...
to wait a while.
If you're willing to wait a while. But then, in those days, you were.
Well, in those days you were, yeah, you were lucky to be competing at all.
Right.
Beat the old punch card equipment we
Yes.
started with.
Yes.
So how did the the user community take to your language?
Well, with regard to George, there were a few internal, that is, users internal to Draper. I'm not aware that anybody outside Draper ever used it. The first serious problem that we attacked was one involving a three-dimensional lead pursuit course for a fighter aircraft trying to shoot down another aircraft. At that point in time, we were operating the MIT's Rockefeller Differential Analyzer, which, as I remember, it had 18 integrators. That was too few.
I see. Okay.
We wrote the differential equations into this program. It took about an hour or two to put the thing together on George, and submitted the tape, and it ran. As I remarked earlier, I'm not sure that we ever looked at the numerical results, so there's no guarantee that it ran absolutely correctly, but in fact, I don't think we had anything to compare it to, but at least it survived.
Right.
And there were, I think, a couple of other programs that used it once or twice for satellite calculations of one sort or another. With regard to the successor Mac, which ran on the 650 and later the 700 series machines, those were used very extensively. In fact, for a while, almost exclusively at Draper for the development of Apollo software and subsequent activities of that sort. That language, as I pointed out to you in the manual, not the manual, but the brief write-up on the thing, used 3 lines of code, if necessary, to represent on the main line the principal symbols, on the line above exponents, and on the line below subscripts. It also had something I didn't comment on, which was vector matrix notation, designed to permit three-dimensional computations of the kind done in dynamic analysis of vehicles and control systems of that sort, which is, I think, one of the principal reasons it got used as extensively as it did.
Right.
It was designed with that kind of application in mind, although it, apart from things like built-in differential equation operations, was not designed exclusively with that domain. In fact, the last Mac program I ever wrote was a simulation of a transfer line in automotive production.
Okay.
It later got translated into Fortran.
Right, right. Well, it sounds like your language was well ahead of its times in terms of the notations and the concepts built in. I mean, Fortran was kind of a step backwards from yours.
Well, yes and no. Fortran was developable into a usable commercial product. I think in some respects it was more general. If you talk about this vector matrix notation and so forth and so on, that is possibly a little bit specialized. but the Mac also, apart from the 650, was developed during the decade of the 60s, primarily for machines that nobody else used. For whatever the reason, we moved from the 650 to Honeywell H800 and H1800 computers. And it was only sometime around 1968 that we finally made the move to IBM 360. But there was no point in trying to push Mac when we were running it on the Honeywell machine because there were no takers.
I see.
It was a rather small community.
Mm-hmm.
I think Mac was actually written once upon a time for, well, that's a side issue, some other computer at NASA Houston's request. But
so a lot of the Apollo code was written in.
Well, the simulations were actually the Apollo simulations, as they finally developed, had really two arms to them. One was the algebraic and the dynamics, the flight path, all that sort of stuff, computation, which was written in Mac. The other was a instruction at a time, digital simulation of the actual operation of the Apollo guidance computer. And those two ran hand in glove and permitted you to simulate in as realistic an environment as you could produce what was actually going to take place in flight. So
I commented earlier, looking back 1969 from where we are today, you really wonder how that Apollo craft ever got to the moon and landed properly.
I don't think it was easy.
I'm sure it was not. The primitive nature.
Although actually I had backed away from the Apollo program at that point in time. I know why in an informal conversation previously I was describing this Mars mission that a few of us tried to plan back in the late 50s. I was enamored of the notion of putting computers in space, and was enamored of, I guess, what you would call artificial intelligence today, although even today I know very little about that subject. But when Apollo came along, I was very, very negative about putting people in the vehicle. In fact, I think I pointed with ridicule at one point to the great claim for the importance of having a man in the space capsule because he was able to fix his own life support equipment, which of course wouldn't have been there if he hadn't been.
Right.
So when Apollo finally came along, I did do, as I said, this executive software, but then backed off into, general areas of, we were managing labs' computer systems at that point in time, and kind of went into that aspect, into operating systems and other stuff before IBM came along with the 360 and the nightmare that surrounded it.
Right. So the basic idea of George was just you.
Yeah.
You decided to do it.
Yeah. Against a bunch of skeptics.
Oh, I can imagine.
In my own ranks, and there was one of the senior Whirlwind people, who I will leave unnamed, that said, well, why would you want to do that? We already have a language for Whirlwind, namely their assembly language.
Right. Well, I know John Backus had the same problems at IBM when he wanted to do
Oh, I'm sure he did,
Nobody
yes.
will ever use this.
Yes.
This was just crazy.
Yes.
And turns out
somehow it caught on.
Well, if you've ever written optal code, which is where I started,
Yes.
it's easy for things like that to catch on, you know?
Yes, yes. Yes, it is. Yes, that's how we started on the 650 with reading in some of the starting code with dials on the console.
Oh, yeah, yeah. Of course, for the 650, that is, I recall the challenge was you had to place the next instruction just right on the drum, so
Yes,
it wouldn't take too
yes.
long to be able to get to it.
Eventually, I wrote an
Got the-
assembler that did that for you, fortunately. So.
Yeah, yeah. Well, you did one of those also.
Oh, yes.
Oh, did you?
One, well, I don't know. I've written in so many different computers, I couldn't tell you.
Right.
But yes, this was.
Well, that was quite a challenge in those days. You got one instruction, you had to change an instruction. Chances are you might just have a
Right.
whole drum revolution before you got
got
the
around
patch.
to it. Well, it had its unfortunate consequences also. When you wrote a program that came close to filling memory, you would read the program in a card at a time, as I remember it, and they became slower and slower and slower as it went through its search to try to find a place to put this thing.
Right. The computer with 1024 tiny words of memory, that's just amazing that you can write a compiler.
Well,
You must have had
you can
fun.
take that home with you if you want to. Donald Knuth, I sent him a copy of this in conjunction with this report that he wrote. He wrote me back once upon a time that he had spent a weekend, and without knowing the Whirlwind language, he had read and analyzed the software.
Oh,
And,
really?
He confirmed that my suspicion that there was one particular error in what I gave him.
Mm-hmm.
And
Don's
so,
an amazing fellow. That
yeah,
makes-
I guess so. Yeah, I've never known him personally, but
no, he's one of the finest minds in computer science. I think.
oh, I know.
Both as a programmer and as a mathematician.
Yes,
He's one of the first
Right.
to really mix both
absolutely.
very, very well. One of the first to produce a book that actually had programs in it,
Yes,
in addition to the mathematics. So the first.
one of the first who recognized there was such a thing as computer science.
Yes, I think that's fair. Put on him. He was one of the first. I noticed you were trained as first a chemical engineer and then an applied mathematician. So
Yes, well, actually, it was a little devious. I graduated with a chem engineering degree at the insistence of my father, and
Oh,
wrote him in the early spring that I was going to switch into pure mathematics.
mhm.
Got a telegram immediately, I'll be on the next train. Well, he came back and talked to the people in the math department and became convinced that this was a reasonable thing to do. But
Mhm.
I spent a year at the Institute in pure mathematics, taking 5 courses, of which each was a prerequisite for the others,
Oh, that sounds
and
cool. Yeah.
culminating with a delightful experience with Norbert Wiener, who I couldn't understand at all.
Well, I'm not sure many could, as a matter of fact.
Right.
Quite a challenge to understand his. I've attended a few of them myself, and formidable characters.
Yes. Yes.
Bunch of formidable characters down there.
Ah, yes.